So thank you for the invitation, Gabriele and Federico. So today I will talk about unbalanced minibatch optimal transport applications to adaptation, which was an ICML paper last year. So this is a joint work with Thibaut Séjourné, Nicolas Courtier, and Rémi Flammary. And so I will start with a quick introduction on adaptation first, just to motivate the problem and how I ended up working on this. And then I will present optimal transport, minibatch optimal transport, unbalanced optimal transport, some statistical and optimization properties, and I will finish with quick experiments. So first, in domain adaptation, what we have is that we have two domains. One target domain where we do not have access to the labels of the samples, and one source domain where we have access to the sample. And so the goal here is to classify the unlabeled target data samples using the source labeled samples. So we want to transfer the knowledge from the source domain to the target domain. And so I will suppose here that we have the same label distribution in the two domains. I will also suppose in another setting where we have a subset of labels in the target domain, the labels of the target domain is a subset of the labels in the source domain. And so the main strategy in using deep neural networks to solve this problem is to align the distributions of the two domains in an embedding. And so one very good algorithm to do that is deep GERAD, which was an algorithm developed in my previous team. And it was coded in Keras that I do not know how to use because I'm mostly using PyTorch. And so I was trying to reproduce their claimed results in PyTorch. And I failed, like I completely failed. I have never succeeded to make it work as good as they claimed it to be. And so in the meantime, I was working on the theory of minibatch optimal transport. And I realized that there are some problems in the definition of minibatch optimal transport that could explain why it worked so bad in practice. Well, not bad, but not as good as they claimed. And so at some point, I just changed one line in my re-implementation and it really changed everything. And that line was the use of unbalanced optimal transport instead of optimal transport. And so today, from this practical experiments, we developed a new theory which explains why unbalanced minibatch optimal transports might be better than minibatch optimal transports. And so this is the other setting that I will consider. So this is partial domain adaptation where I have extra classes in the source domain. So here it should be the stars. The stars are in the source domain, but not in the target domain. So now I will introduce optimal transport. So what do we need? We need two distributions. So here I will consider probability distributions. But usually it's just distributions of the same mass. And I need a ground cost on the space, on the data space. And so what I want to do is to transport the distribution alpha towards beta. And as the problem is symmetric, the optimal way to transport alpha to beta is also the optimal way to transport beta to alpha. So to find the optimal transport way to move alpha to beta, I will use the Kantorowicz primal formulation. So people on Zoom might not see well, but no, not people in Zoom, but so this is pi1 and pi2, and so I'm looking for a joint probability distribution pi, which minimizes the displacement cost from alpha to beta, and the marginals of the probability distributions pi, so pi1 and pi2 need to meet the marginals, the input distributions alpha and beta. So pi1 has a constraint to be equal to alpha and pi2 has a constraint to be equal to beta. And so this is the case for when I have continuous probability distributions. But when I have the distributions which are sum of Dirac's, so discrete probability distributions, so I require a ground cost matrix C, which is now, it's a matrix where each element of the matrix is the distance between two elements of one element of the source domain and one element of the target domain. And so in this case, the optimal transport problem becomes a linear program. that as an optimization scheme, you might know a lot of it. So it has still some constraints on the transport plan pi. Yeah, so pi now is now a transport plan, which might still be as a priority distribution, a joint priority distribution. And its marginals now need to be equal to the priority vectors A and B, which are the priority weights of distributions. So regarding the optimal transport problem, the control-rich problem, so there is always a solution. Takes, for example, alpha times the tensor product of alpha and beta. The probability product P and C, pi and C is linear in the ground cause C and in the transport plan pi. Unfortunately, so to solve this problem, we use the associated dual and the simplex algorithm of the associated dual, and it's cubical in the number of samples. So the bigger numbers of samples you have, the longer it is to compute the solution. And so what is interesting about optimal transport is that it can define a metric between priority distributions. If you consider the ground cost as a ground metric, then you can define the basal line distance, which is defined as you can see here, and it defines a metric between priority distributions alpha and beta. I will quickly talk about the case where I have data which lie in 1D. So I consider two priority distributions in 1D, and I sort them. I also suppose that they are uniform. And so in this case, as they are sorted, the optimal transport plan is the identity plan scaled by a uniform weight. So this is a case for uniform weights only. And so a quick time experiment to show the problem of the computational complexity. As the number of samples grow in the distributions, the times to, we don't really see it well here. So I consider also the classical optimal transport problem, but also the entropically regularized optimal transport problem, which is known to be easier to code and to have a better sample complexity. And we saw that it is quadratic in the number of samples. But the key home message is that it cannot be used in a big data scenario. So when you have data sets with millions of images, you cannot use optimal transport directly. Well, for two reasons, actually. The first one is because it will be really long to compute the solution, especially as you're training a neural network and you need to do it at every step of your optimization training. But also because at the memory level, because you will need to store the ground cost matrix with which have like 1 million by 1 million dimension, and this is not going to suit a GPU.
Sorry.
Yeah.
To be sure, the number of samples is the same as the number of.
Oh yeah. In this classic two examples, I consider the same number of samples, and in the case where you have n1 sample and n2 sample in the two distributions, it will be n1 well the maximum between n1 and n2 cubic log of the maximum of the three. So basically, you take the complexity of the biggest number of samples. So one way to decrease this, to alleviate this problem is to use minibatch approximation. So this was used empirically in 2018 in two different problems. So the first problem was for domain adaptation and the second for generative models. So the idea is simple. We select m samples without replacement and randoms in the two domains. We give them uniform weights. At least this is what these authors did. And they compute the optimal transport cost between the uniform minibatch distribution. And so if you can also average several minibatch optimal transport terms, as you can select many minibatch couples. And but the complexity now is cubical in the minibatch size. So going back to a problem where with millions of images, now using minibatch OT, we have a computational complexity of 500, like if it is your minibatch size. So it's really lower. However, when you do this, you change the problem. You didn't compute the optimal transport cost anymore. What you compute is the expectation of the optimal transport cost between minibatches. So you select a lot of, well, all possible minibatch couples, and you average the optimal transport cost between all these minibatch couples that you have drawn. So this can be defined for any optimal transport variance, the classical one, the entropic regularized optimal transport variance, the Gromov of a certain, if some of you are working on graph, maybe you're aware of this variance, but for any variance. And so I investigated before for only optimal transport. And so you have two ways of estimating this quantity. You can use a complete estimator, or you can use an incomplete estimator. The complete estimator is just the average of optimal transport between all possible minibatch couples. But this is not practical in practice, tractable in practice, because you have a combinatorial number of terms to calculate. So even if you can use a parallelism on CPU, it would be just too long to compute, or on GPUs. However, what you can do is an incomplete estimator, and this is what people use in practice, and what they use instead. So here, what we do is that we average k optimal transport between k minibatch couples, and in practice, k was equal to 1. So you just draw one minibatch in the source domain and one minibatch in the target domain, and you compute the optimal transport cost between the two minibatches. So you can also define a complete estimator for the transport plan. And when you study, you can also draw a closed form solution when data lie in 1D. And so this is interesting because it will help us to understand what happens on the minibatch optimal transport plan. And so as we see, as the minibatch size decreases, the number of connections between samples of the two distributions increase. So it means that one element will be spread to more elements of the target. One element of the source will be more spread to many elements of the target domain. And when m equals to 1, all the weights are uniform. So the number of connections increases and the intensity gets uniform. This is a phenomenon that we also see in 2D. And so here we actually put that I have two clusters in the source distribution and in the target distribution. And I can see that while I perfectly recover, while transports clusters between clusters for the original optimal transport cost, the minibatch approximation creates a lot of connections between the clusters from the source to the target domain. And so this is a problem of the domain adaptation setting, because as we do not have the levels, we will have to draw randomly at uniform samples in the two domains. And so it creates, it will create the marginal constraints in the minibatch samplings create connections between classes. And so this might explain why I was not able to reproduce the results from deep GERAD in practice. And basically, this is the reason why. So to alleviate this problem, I want to use unbalanced optimal transport. So unbalanced optimal transport is really close to optimal transport, and it's at the exception that we do not have any more constraints on the probability distribution pie, on the transport plan pie. So now I'm just looking for a positive measure on the data space, x times y, and I replace the hard marginal constraints by soft penalties. So the constraints on pi1, which need to be equal to alpha, and pi2, which need to be equal to beta, are now replaced by soft penalties. So I also use an entropic regularization term. And the reason is that it is really easier to compute the solution using the entropic regularization, because we have like a 7-line algorithm in Python which does it for us. So it's really convenient. And now the function is only linear in the ground coast. And one also important aspect of using the entropic regularization is that we have a unique solution, and it will be useful for optimization properties later.
Can I ask you a question? Is there a reason why you use the same marginal penalization for both alpha and beta?
You could use a different one. It would be correct to do it. The reason is it was easier to tune. You will see in the algorithm that if you put T1, T1 and T2, you will need to play with them in practice, and it will just be like a nightmare to find the correct hyperparameters. So why do I want to use unbalanced optimal transport? Well, I want to use it because it has some robustness properties which are not shared by optimal transport. And so this lemma, basically, I will go to the next slide. So this lemma just says that if I have an outlier that pollutes, if I have a distribution which is tainted by an outlier, so the green point tau here, the green point, and that this outlier moves away from the distribution, and that I want to transport the distribution alpha to the same distribution, but with the green sample. So I can see that when the green sample moves away from the distribution, the optimal transport cost increases. But this is not the case of unbalanced optimal transport variance. And the reason is because as it is costly to transport it, unbalanced OT is lazy to do it and just remove it. So this is really what I want to use, because the idea now is that as minibatch optimal transport created connections between classes because of the marginal constraints, if I relax the marginal constraints, maybe, this is what I hoped, maybe the connections between the different clusters would be alleviated, mitigated. And indeed, this is what we can observe on these 2D examples. So now we have two different clusters in the two distributions. So this is the source distribution, this is the target distribution. Those clusters are well balanced in the source, but imbalanced in the target. So I have only 3 red samples in the first cluster and 7 green samples in the second cluster. And so the entropic optimal transport or optimal transport, it would be the same. And minibatch optimal transport, they create a lot of connections between the different clusters, especially as I have a shift in the labels, so in the clusters. However, this is not the case of unbalanced OT because it is simply too costly to transport the first cluster to the second cluster if I play correctly on tau. So I need to find the correct tau. And when tau is too small, the problem that we can have in practice is that we can have lazy gradients, which will slow down the training of your neural networks. So what about optimization learning properties? So the complete estimator and incomplete estimators, when I suppose that I have IRD data samples, are unbiased estimators of the expectation of minibatch optimal transport. So this is the first point, and it is the second point is that it is strictly positive for non-trivial priority distributions. So if I suppose that I have 2 priority distributions which are not of mass 0 or not 1 Dirac, well then the unbalanced optimal transport cost for this will not be equal to 0 when I consider the same distribution. So I lose the metric properties. So it's not a metric anymore. So this is a difference with optimal transport. I cannot have with minibatch and minibatch unbalanced OT a distance between priority distribution. However, one good aspect is that I have an unbiased estimator. So I'm losing on one side, but I'm winning on another. So maybe in practice, it's still interesting. And so for all the theorems now, I just consider that I have 2 probability distributions with compact supports. Because it's just easier to write the proofs. And it is also the case when you deal with images. So the first result is that I have a concentration bound between my incomplete estimator and its expectation. So as I am using an incomplete estimator in practice, I want to know how far it is from its expectation. And so if I consider a fixed minibatch size, I see that when I consider a bigger number of samples and which linearly increases, as well as a minibatch k minibatch couples k, well then the incomplete estimator would just get closer to its expectation. And so now regarding optimization properties, what I want to do with a neural network is to fit a parametric model beta theta. So I have 2 distributions, alpha, which is basically which is an empirical distribution, and I have a parametric distribution beta theta. And I want to find the best parameters of beta theta, which will minimize the unbalanced minibatch optimal transport cost. And so I would like to optimize this loss function with stochastic gradient descent. But to justify its convergence, I would need to exchange the gradients and the expectations. And to do that, I would like to use Hovding lemma. Not Hovding lemma, Lebesgue lemma, differentiation lemma. But I cannot, because in the case of unbalanced OT, I am not differentiable. So what I used instead is a new notion of regularity, which is the clock generalized gradients. So Clark was a Quebecois mathematician, and he developed this new regularity for a locally Lipschitz function. And under some extra hypothesis on the ground coast, I can indeed exchange the gradients over parameters and the expectation over minibatches. And so I would, stochastic gradient descent would converge. And this is not the case for minibatch, for optimal transport, original optimal transport, because of a bias in the estimator. So I quickly finish on experiments. So our algorithm Jumbot aligns a joint law between the embedded samples of the two distributions. And so we want to use like DJDOT, and we want to use unbalanced OT in place of optimal transport at the minibatch level. And so we consider two different images of the two domains. For instance, here this is SVHN and here this is MNIST. We embed them, so we get their their extracted features. And then using their extracted features and the predictions and the labels in the source subdomain, we define a new ground cost, which will align the two distributions. And we also use a typical cost-entropy on the source domain. I do not go into the details of the algorithm too much. And so in the case of partial domain adaptation and domain adaptation, we are able to outperform state-of-the-art results by at least 4% on domain adaptation and 2% on partial domain adaptation. And compare DeepJDOT and Jumbot, we see that we are able to improve DeepJDOT's results by 6.5% in vanilla domain adaptation and 16% for partial domain adaptation. So if we have a look at the extracted features, we see that Jumbot is able to create well-defined clusters, while DeepJDOT has some overlaps between classes, as we can see here or here. And this explains why a small drop in performances and the effect of minibatch optimal transport. So another advantage of using Jumbot that we can see in this graph, so the batch size sensitivity analysis, is that when the minibatch size decreases, the performances of Jumbot remains pretty much constant, while the performances of DeepJDOT can decrease by 6%, if I recall correctly. Yes, it is 6%. So you can find the full details in the paper, and I thank you for your attention.
Thank you, Kilian, for a very, very interesting talk. Any question from the audience or Zoom? I have a question on that. And it's back to the question of the penalty terms.
Okay.
So you said that basically, you know, decoupling them and having them separate would like probably increase, you know, the size of the parameters to tune
yes.
the model, so on and so forth. Have you like tried to do that in practice? Like, so
the problem is that Jumbot has already 6 hyperparameters.
Okay.
And when you deal with the real world images, it's already very long to find the correct one. So no, I haven't.
Okay.
But I know that some people do T1 here and T2, where T2 is really big compared to T1. And the reason is that in partial domain adaptation, you are sure that you want to map the target to the source distribution.
Yeah.
But some source distribution you might not want. If you have a shift in the mini batches, you might not want to fit them to the target distribution. So this is what they do. They take a big T2 and a small T1.
So there is more penalty on the
yes.
violation of the target distribution.
Yes, exactly. Yeah.
Interesting. I mean, from an optimization perspective, I don't do optimal transport, and I think the choosing the right penalization often does impact a lot the result, but also it's true that when you have to learn like a lot of parameters, it's something that I think you cannot do.
Yes,
right? Like
yes.
It's nice in theory, but in practice it doesn't work. And like choosing the same probably, I guess, as you showed, like turns out to be like quite efficient, in fact.
Still long to
yes.
I realized that well, a friend of mine actually we computed my experiment, and he found that the hyperparameters that I took were not the best ones. Mm-hmm. So he was able to increase my results with the same algorithm by just choosing other hyperparameters. So yes, it was already complicated, and it looked like even in the published paper I didn't have the correct ones. So I was not really eager to get another extra hyperparameter to tune.
Yeah. So you mentioned that to calculate the optimal transport between two.
Okay, wait, I didn't really hear correctly, so I'm fine if you just drop the mask to ask a question.
So I want to say, so in your talk you mentioned that the optimal transport between two continuous distributions, two discrete distributions. So is there a way to calculate the one continuous and the one, for example, for the water space?
Yes, okay. So there are two ways to do that. If you want to use the exact optimal transport, you might use what is called the Kantorowicz-Rubinstein duality theorem, where you approximate the dual potential by a neural network. But we in the community of optimal transport, we know that you do not really approximate the optimal transport cost, the Wasserstein distance. So as you can see, for like WGAN or any variance, we know that they do not really compute the Wasserstein distance. The approximation is really bad and is really far from what it should be. Another solution would be to use the entropic optimal transport, where you can approximate it using some elements of kernel theory. So it is in a paper which was written by Ojenve in 2016, and maybe it was stochastic optimization for entropic optimal transport. You can find more details, but yeah, those are the two main ways to approximate the continuous probability distributions pi.
Okay.